Hi everyone. In this video I'm going to talk about dimensional analysis. Why should we study dimensional analysis? Although many practical engineering problems involving fluid mechanics can be solved by using the equations and analytical procedures, there remain a large number of problems that rely on experimentally obtained data for their solution. In fact, it's probably fair to say that very few problems involving real fluids can be solved by analysis alone. The solution to many problems is achieved through the use of a combination of theoretical and numerical analysis and experimental data. Thus, engineers working on fluid mechanics problems should be familiar with the experimental approach to these problems so that they can interpret and make use of data obtained by others, or be able to plan and execute the necessary experiments in their own laboratories. An obvious goal of any experiment is to make the results as widely applicable as possible. To illustrate a typical fluid mechanics problem in which experimentation is required, consider the steady flow of an incompressible Newtonian fluid through a long, smooth-walled, horizontal, circular pipe. An important characteristic of this system, which would be of interest to an engineer designing a pipeline, is the pressure drop per unit length that develops along the pipe as a result of friction. Although this would appear to be a relatively simple flow problem, it cannot generally be solved analytically without the use of experimental data. The first step is the planning of an experiment to study this problem would be to decide on the factors or variables that will have an effect on the pressure drop per unit length. We expect the list to include the pipe diameter, the fluid density, fluid viscosity, and the mean velocity at which the fluid is flowing through the pipe. Thus, we can express this relation, which simply indicates mathematically that we expect the pressure drop per unit length to be some function of the factors contained within the parentheses. At this point, the nature of the function is unknown, and the objective of the experiments to be performed is to determine the nature of this function, f. To perform the experiments in a meaningful and systematic manner, it would be necessary to change one of the variables, such as the velocity, while holding all others constant, and measure the corresponding pressure drop. This series of tests would yield data that could be represented graphically, as illustrated in Figure A. It's to be noted that this plot would only be valid for the specific pipe and for the specific fluid used in the tests. This certainly doesn't give us the general formulation we are looking for. We could repeat the process by varying each of the other variables in turn, as illustrated in figures B, C, and D. This approach to determining the functional relationship between the pressure drop and the various factors that influence it, although logical in concept, is very difficult. Some of the experiments would be hard to carry out. For example, to obtain the data illustrated in figure C, it would be necessary to vary fluid density while holding viscosity constant. How would you do this? Finally, once we obtain the various curves shown in figures A, B, C, and D, how could we combine these data to obtain the desired general functional relationship between the pressure drop, the diameter of the pipe, the density, viscosity, and velocity, which would be valid for any similar pipe system? Fortunately, there is a much simpler approach to this problem that will eliminate such difficulties. We will show that rather than working with the original list of variables, we can collect these into two-dimensional combinations of variables called dimensionless products or dimensionless groups. Thus, instead of having to work with 5 variables, we now have only 2. The necessary experiment would simply consist of varying the dimensionless product of rho v d over mu and determining the corresponding value of d del p over rho v squared. The results of the experiment could then be represented by a single universal curve as illustrated in this figure. This curve would be valid for any combination of a smooth-walled pipe and incompressible Newtonian fluid. To obtain this curve, we could choose a pipe of convenient size and a fluid that is easy to work with. Note that we wouldn't have to use different pipe sizes or even different fluids. It's clear that the experiment would be much simpler, easier to do, and less expensive. A fundamental question we must answer is how many dimensionless products are required to replace the original list of variables. The answer to this question is supplied by the basic theorem of dimensional analysis that states the following. If an equation involving k variables is dimensionally homogeneous, it can be reduced to a relationship among k minus r independent dimensionless products where r is the minimum number of reference dimensions required to describe the variables. The dimensionless products are frequently referred to as pi terms, and the theorem is called Buckingham pi theorem. The pi theorem is based on the idea of dimensional homogeneity. Essentially, we assume that for any physical meaningful equation involving k variables, such as u1 equals f, u2, u3 to uk, the dimensions of the variables on the left side of the equal sign must be equal to the dimensions of any term that stands by itself on the right side of the equal sign. It then follows that we can rearrange the equation into a set of dimensionless products or pi terms in this form.